All right, so yesterday we took a look at section 7.3 and we were able to talk about this idea of translation on the S-axis. And before I forget, let me drop a link in the chat for that table just so we all have eyeballs on it. All right, I've got the table up. You'll shortly have that table up. But what we had was this idea that if we have an exponential function multiplied by the thing that we want to take the Laplace transform of, it turns out that that exponential function causes us to experience a shift or a translation on the back end. Okay, so like after we've applied the Laplace transform. We did do a few practice problems where we took a look at just doing the translation in the forward direction, like applying the Laplace transform. And then we sort of went backwards where we were finding the inverse Laplace transform. We highlighted a few strategies that might be beneficial in terms of making sure we don't make any sort of small mistakes that we would be really sad about when we're computing these, using the table to find the different transforms. And then we finished the day with solving this initial value problem. And we sort of talked about, applying that Laplace transform to find the solution, finding that solution, but then having to convert it back to an expression with t so we could have our solution in the realm that we were asked. And then at the very end, I said it would probably be good practice for Thursday's exam to take a look at this problem and kind of see like where you are finding yourself getting tripped up and where you're finding yourself having maybe more strengths than you thought you would have. Okay, and so let's go ahead and get started. So while I'm writing out step number 1, all right, and so we'll just sort of group this idea of apply the Laplace transform. And initial conditions to find our y of s, our uppercase y of s. All right, and it sort of happens this way, like the more we do certain problems, as we layer on more and more strategies, we realize that we can actually clump some of our steps that were previously separate into just like a single step, right? And so you'll see that this is a little bit more condensed than it was in 7.2, where we had these as like different steps. But we've got our left-hand side, right? And there are set things that we put in every single time for that left-hand side. And then for the right-hand side, this is where we use our table, and we have to be really careful about that. Okay, so I'm going to go ahead and write out the left-hand side. And if you could, if anyone, one of you could put the Laplace transform for the right-hand side into the chat, hopefully we'll meet in the middle somewhere here. And be able to write out what we have.
Is the right side going to be 1 over s plus 1 over s plus 1?
Do we have any agreement on that? That looks right to me. The 1 becomes the 1 over s, and the 1, or the e to the negative t becomes 1 over s minus -1, right? So that used to be like in the actual table, it's a negative, but because it's a minus minus, then we get that plus, right? And so what we've got on the left-hand side, we know that we can go ahead and plug in everywhere we see a y of 0, we can plug in 0. Everywhere we see a y prime of 0, we can also plug in a 0. And so this one's quite nice because a lot of things sort of fall away. This is going to go to 0. This will go to 0. This will go to 0. And at the same time, I can sort of clump all of my terms with the y of s. And it turns out all the ones left have a y of s. So we've got 1, 2, and 3. And if we go ahead and factor that out, that y of s will be left with s squared plus 4s plus 6 equals 1 over s plus 1 over s plus 1. Right? And so now at this point, the only thing we need to do to isolate our y of s is we're going to go ahead and divide that s squared plus 4s plus 6 away. All right. And sort of thinking ahead, s squared plus 4s plus 6, is that reducible or irreducible?
Irreducible.
Yeah, that one is going to be irreducible, right? And so when we think about, oh, we're going to need partial fractions to get this back into our y of t, we want to make sure that we accommodate for the fact that this one is going to actually have a linear factor on top. Okay. And so when I sort of divide things over, I'll end up with 1 over s times s squared plus 4s plus 6 plus 1 over s plus 1 times s squared plus 4s plus 6, right? Now, I know that if I want to combine these into a single fraction, I'm going to have a common denominator. And so what I can sort of start to envision, if I cheat a little bit here, is that I'm going to need to multiply the first fraction by s plus 1 over s plus 1. Right? I'll go ahead and put that in parentheses to remind myself I'm going to need to distribute things. And then for the second fraction, I'm just going to need to multiply by s over s. And so that, my friends, gives us y of s equals, what do we have? S. Well, we're going to have s plus 1 plus s. So we can actually say 2s plus 1 for our numerator. And then in the denominator, we have s times s plus 1. Those are both linear. And then I have an irreducible quadratic, right? Now, I know that because I have to apply a Laplace transform here, that it would probably be beneficial for me to think about that partial fraction decomposition, right? And so I can already start to think I'm going to need 3 different fractions, right? 1 for the s, 1 for the s plus 1, 1 for the s squared plus 4s plus 6. And based off of yesterday, what do we know about these numerators here? What are we going to have for these numerators?
You mean like it'll be 2 constants and then 1 linear term?
Perfect. Yep. We're going to have some constant, another constant, and then the last fraction will have a CS plus D situation, right? Now, I know this question is in the book, right? If you've looked in the book, you know that they sort of set this up. They do the order of this middle part a little bit different, but at the end of the day, we end up with 2s plus 1 in that numerator. They do, however, skip all the steps for that partial fraction decomposition, which is actually kind of nice because they give you like an end goal, like this is what you should get for your numbers, but they don't really show you how to get there. And I think that that's a really good place for some of us who always find like we get caught up in the computation of things to sort of challenge ourselves and make sure that we can arrive at the same answer we know we're supposed to get, okay? And so let's go ahead and do a little bit of that setup for the partial fraction decomposition. And we can sort of group this in that second step where we say we're actually going to apply the inverse Laplace to obtain our lowercase y of t. All right. And so we'll begin with a little bit of partial fraction decomposition. I'm only going to write the numerator here. And so, because I know that once I make the denominators the same on both sides, I don't need to worry about them. So on the left-hand side, I'm going to have 2s plus 1. And on the right-hand side, I'm going to have a times s plus 1 times s squared plus 4s plus 6 plus b times s squared plus 4s plus 6 plus, I think this is a place where parentheses are really important, cs plus d times, I'm going to have to multiply by both of these. So I have an s and an s plus 1. Right. Now, I feel like, I've made several suggestions around sort of techniques on how we can solve this. For the folks that are in the space today, what ideas do you have? Like, what are some things that you found really work well for you in setting these up and solving them? In other words, for this problem, how would you move forward?
I know it's a little bit more work, but I usually put them in a matrix because it just prevents me from making any errors, but I know you got to FOIL all this stuff out. So
Okay.
You could also set s equal to 1 and s equal to 0.
All right. So I think that is actually a really valuable thing. I know we've been doing ours with substituting clever numbers, right? We would maybe choose s equals -1. We could also choose s equals 0. But is there anyone in this space today who's like, I would really like to see the matrix setup, because I know that we haven't actually, we sort of just like talked about it, but we haven't done one together. Is there anyone in this space who would find value in seeing what it looks like to have a matrix part worked out?
Yes, please.
Okay, cool. I feel like that's sort of a connection between like linear algebra. If you just sort of happen to remember, it's great, but otherwise we haven't had a chance to practice that. Okay, and so we do indeed, if we are going to do the matrix solution, we do have to FOIL everything out. Okay, so this is where we really need to be very careful about our distribution over here. I think the first one is probably the hardest. The second one is pretty straightforward, I think. And the third one is more of a basic like FOIL problem, right? And so if we were to FOIL everything out, right, we're going to get, let's see, 2s plus 1. That stays on the left-hand side. And on the right-hand side, let's go ahead and distribute that s to all three terms here, and then we're going to add the 1 distributed to all three terms. Okay. And so we'll get s cubed plus 4s squared plus 6s plus s squared plus 4s plus 6. All right. So all I've done is just sort of multiply and distribute over here. I'm going to go ahead and do the same thing with the b term. So this s is going to distribute it into all of those. And so we'll have b s cubed plus 4s squared plus 6s. And then we'll do the same thing over here, where I'm going to actually say this is s squared plus s. And then I'm going to FOIL out what we have here. Okay. So plus cs cubed plus cs squared plus ds squared plus ds. And now I'm going to distribute the a into the first one. I'm going to distribute the b into the second one. Okay. Now I notice that I have some cubic terms and I have some quadratic terms, but I don't have those on the left-hand side. And so at the same time, I'm going to write a little bit of extra stuff on the left-hand side. I'm going to write 0s cubed plus 0s squared plus 2s plus 1 equals, and now I distribute. So as cubed plus 5as squared plus 10as plus 6a. All right, let's do a quick double check. Does that seem to work out with the distribution here? As cubed plus. Yeah, because I've got the s cubed, I've got these two that have the s squared, the 6s plus the 4s, and then just the 6 at the end. Okay. All right, we'll do the same thing with the b terms, plus bs cubed plus 4bs squared plus 6bs. And then we'll list out the last ones. We had cs cubed plus cs squared plus ds squared plus ds. Okay. And so once we have those, my suggestion to you would be to go through and group all of your like terms. Okay. And so for example, we have 0s cubed equals as cubed plus bs cubed plus cs cubed, and there's no s cubed with a d. So I can write that as one equation. And I can have 0 equals a plus b plus c. All right, let's go through the quadratic ones. 0s squared equals 5as squared plus 4bs squared plus cs squared plus ds squared. So this one actually has 4 terms to it. 0 equals 5a plus 4b plus c plus d. Okay. This one will correspond to all the terms underlined in that color. All right, we've got the linear term. So 2s equals 10as plus 6bs plus ds. So notice there's no c term this time. So we've got 2 equals 10a plus 6b plus d. And we've got one last equation here where we have 1 equals 6a. And is that the only one that has just a constant? I think it is. So we'll get 1 equals 6a. Okay. So this should actually not look different than if you were to say solve with a system of equations, right? We have 4 equations now. We have a yellow one, a red one, a green one, and a purple one. And we could use algebra, we could use elimination, substitution, whatever we wanted, but we would be able to sort of work through the algebra. But with the matrix, the only difference is we sort of have to organize the way that we are writing the equations and making sure that everything has a spot, including zeros for placeholders where there is maybe no particular one of those letters, okay? And so if we were to set up a matrix here, before we do that, let's go ahead and put all of these equations in order. Oh, this is much better. Okay, good. So if I were to put them in order, as a mathematician, I'm going to start with my A, and then I'm going to move to my B, and then I'm going to move to my C, and then my D, and then I'll have my equal sign, and then whatever numbers left on that side. Okay. And so for the first one, this yellow equation will become, maybe we do it this way. This yellow equation will become A plus B. Let's do this one better. 1A plus 1B plus 1C plus 0D equals 0. Okay, so that's just sort of like an organization step. If I did the same thing with the red one, I would get 5A plus 4B plus 1C plus 1D equals 0. Oh, is it not sharing anymore? Hold on. Oh, there we go. Okay. All right, for the third one, if I line them up in order, I would get 10A plus 6B plus 0C plus 1D equals 2. And then if I line up the last one, I'll get 6A plus 0B plus 0C plus 0D equals 1. Okay, this is in effect your matrix, but all we're going to do is grab the numbers, right? A matrix is a tool to help us look at these. Now, for those of you who have been doing this using a matrix, is there an online matrix calculator that you found to be really helpful?
I use matrixcalc.org.
Okay, yeah, that's the
It's
first one
pretty
that
good.
popped up in my chat, so, or in my search. So let me go ahead and drop a link for that in here. All right. Cool, cool. All right. And so the link that I sent is just for like the landing page. But what you're going to do in the left-hand column, there is a place that says solving systems of linear equations. You're going to go ahead and click on that, and the screen is going to look a little bit different. All right. And so all we're going to do is we're going to take the numbers that we have and we're going to type them in. All right. And so let me actually stop sharing this screen for a moment. Let me share my other screen. All right. So does everyone see this right now? Okay. And so what we're going to do is we're just going to type in the numbers that we had from our equation. All right. So we have 1, we have 1, 1, 0, and 0. So that stands for 1A plus 1B plus 1C plus 0D equals 0. Okay. What numbers should I type in for that second line? Yep, we're going to start with a 5.
4, 1, 1, 0.
0. Nice. All right. If you have a TI-84 or like any sort of TI calculator, like the graphing ones, they also do matrices. So you can put this on your calculator as well, if you happen to still have one. All right, that third line should be 10, 6, 0, 1, and 2. Perfect. Thank you, David. And the last one should be 6, 0, 0, 0, and 1. Okay. Now, as it stands, it happened to be already set up for the one that we wanted, but you can always add cells, you can delete them, so you can modify it for whatever question you're working on, okay? But I would make sure that the layout here looks like the layout of the equations that you wrote there, okay? All right, so from here, we can have it solved by Gaussian elimination. That's probably the maybe the easiest way, most similar to what you would do by hand. All right, so this is probably where you remember a little bit from your linear algebra. I think every instructor is a little bit different. Some instructors make you do all of this work first. All right, but I'll give you a chance to kind of look at that on your end. But basically, the goal of something like a Gaussian elimination is that you're trying to make it so that you have sort of a main diagonal going on, and then you have these zeros down here. Okay, that helps you find like one variable at a time. But where you probably want to go is the place where it says the answers, right? It tells you what your X1, your X2, your X3, your X4 all are. And those should match with what we have in the textbook as well. Okay. So I'm going to stop sharing this screen, but also give you a moment to type in your own numbers and make sure that you, if there are any questions about how to use this tool, that we take a moment and answer those right now. But I'll go ahead and write these answers down in our notes while we're doing that, okay? All right, so we've got our yellow. Now, if you're wondering like how you might show me your work here, I think some of us have actually been writing it in the matrix. And so that might look something like, let's make sure we get these numbers right. 1, 1, 1, 0, 0, and then 5, 4, 1, 1, 0. 10, 6, 0, 1, 2, 6, 0, 0, 0, 1. Right. And from here, you'll get a value for A. I think the internet said that that was 1/6, which makes sense because we have that purple equation, which makes it really easy for us to find our A value. We've got a B value of 1/3, I believe. We've got a C value of -1/2. And we've got a D value of -5/3. Okay. And so all of this is to say that we can go back into our original solution, put back in our A, B, C, D, and now we can go back and use the table to help solve. Okay. Before we finish this question up, are there any questions about the matrix type solution? All right. Well, let's go ahead and fill these values in so that we can take our inverse Laplace. So we're going to be finding the inverse Laplace of A, which is 1/6 over S, plus B, which is 1/3 over S plus 1, plus CS plus D. Now, I notice that I have a negative as well as a negative. So I have a few options. I can write it in as -1/2 S minus 5/3. Or if I'm feeling like I'd really rather not work with so many negatives, I can factor that negative out to the front. Okay. And I believe that that is the technique that your textbook uses. And so that's why they have the 1/2 S plus 5/3 in that numerator. Okay. Just because they factored that -1 out to the front. And that is over S squared plus 4S plus 6. All right. Now the first two, when we're taking that inverse Laplace, I feel like the first two are pretty straightforward, ones that I would expect you to look at and be like, oh yeah, I totally know how to do that. But I think the last one, this one, maybe takes a little bit more thinking here. Okay. And so when we think about using our table, I think we saw this trick one time. Does anybody remember what we need to do for this last term in order to be able to match it to something in the table? Yep, we could start to separate them, but I think we're still going to be a little bit stuck in the sense that we don't necessarily have something in the table that looks like a regular quadratic, right? A quadratic with a linear term. So I think that there's still a little bit more work we need to do for these last two once we've separated them. Let's go ahead and add another page to give ourselves some space. All right. Well, while we're thinking about that, I think that this first one over here, that 1 over s, that's going to correspond to line number 1 in our table, right? That one's not too challenging. The second one is going to correspond to line number 2. Maybe we make a note to ourselves here that a equals -1. Right? I could see that being maybe a potential sign mistake as we try and feel the time pressure of an exam. These last two, what is that strategy? Well, we got to take these denominators and we have to complete the square. Okay. So I think we did one example like that, but that was sort of like a few days ago before the weekend. And so with this completing the square, we really want to think about like, what is it close to? Is it close to a perfect square? And if it is, then we can use the ones like row 19, row 20, row 21, row 22, depending on what the sign is there. Okay, exactly. And so if we take this s squared plus 4s plus 6, and sorry, my organization is like all over the place right now. And we say, what is that close to? We might notice that it's close to s squared plus 4s plus 4, which would be really lovely because that's a perfect square. But in order to get from 4 to 6, we just add 2. Right? And so the first 3 terms we can rewrite as s squared, s plus 2 squared. And then afterwards, we'll have our plus 2. Okay. So that part corresponds to that. And this plus 2 just kind of hangs out. It's like, here's our almost perfect square. Okay. Now, looking at the signs here very carefully, should we be looking at a sine and cosine, or are we looking for a sinh and a cosh situation?
This would be sine and cosine, line 19 and 20.
Exactly. And this is going to be a line 19 and 20 situation because this plus sign right here, okay, this plus means we're looking at sine and cosine, not a sinh and a cosh. Okay. If, however, we had a negative sign here, then we would be looking at line 21 and 22. Okay. All right, let's do one last thing for ourselves, knowing that we're writing as s plus 2 squared plus 2, and that we're going to use line 19 and 20. Tell me what the a value is. Tell me what the b value is.
They're both 2, right?
Let's see, in the formula, it is s minus a squared. So we're actually going to have a be a -2. And in the formula, we have plus b squared. That means that 2 is actually b squared. And so our b is actually going to be the square root of 2. Okay, so it's these small things where we just have to make sure we match up the numbers accurately, right? And so if that's like too much work to do as you're actually taking your inverse Laplace, set yourself up for success by like thinking those through before you plug them in, okay? All right, I think we are down to the almost final line here, maybe one more after this. But if we use line number 1, then we're going to end up with 1/6 times 1 plus 1/3 times e to the -t minus, let's see, if we use line number which one are we using? Which one should we use for number 19 or for that third one right there? Like this one right here.
That'd be line 20.
Okay, so line 20 has an s minus a here. Do we have an s minus a in our numerator? Right, because whatever we have has to match entirely. Not sure that we have the full line there. Like right now we have s over s plus 2 squared plus 2. And over here we have that 5/3. Right. Now, if you've looked in your textbook, you might notice that their line, that last line that they have, or the second to last line, is a little bit different than what we have over here. And so this is where, like, when you're reading those higher level textbooks, a lot of times they skip these steps, and it's really important to be able to connect the dots. Like, just because it's there in the textbook, well, maybe we need to figure out the reasoning, like how did they get from this line to that line, okay? And so one thing, if we want to use line number 20, in the numerator, I also am going to need an s plus 2. Right? That's the problem right now. I need an s plus 2 in the numerator, and I don't have that. Well, let's kind of backtrack a little bit, right? Over here, we had s, 1/2 s plus 5/3, right? So we sort of had this like plus a little bit. I wonder if there's a way that we could, I don't know, get a little bit more from that 5/3. So instead of splitting it like 1/2 s and then the plus 5/3, I wonder if we could have written our numerator a little bit more cleverly. And that cleverness, I wonder how that could have gotten us to a +2 up here. This would be a good place to think about how we split things, right? Because ultimately over here, I think we're okay in the second one, but like, how do we match that middle term, right? That really is the question. So it turns out, if I go ahead and simplify this part, I'm going to borrow. Okay, so we're going to go back to this idea of borrowing. I'm going to borrow some terms so that I have a +2 in this numerator. Now, if I have a +2 here, okay, bear with me here. If I have a +2, but it was really times a -1/2, then really it's -1/2 times 2, which is -1. So I borrowed 1 from the 5/3. 5/3 minus 1 gives me 2/3. Okay, so when you look, if you're looking in your textbook and you're like, how did they just pull this magical 2 out of there? All right, one thing, first of all, this +2 is not the same as this +2. Like, we didn't just add 2 and call it a day. Okay, we actually borrowed from the second term, right? And we could do it at this step, or we could have done it earlier. But at some point we had to create this +2. So we just took the 5/3 and said, well, one of the 5/3 will go over here, like 3/3, and then the other 2/3 will stay over here. Okay. Now I think there's one last thing we need to do to the last one to be able to match that to the table. And in particular, we need to have a numerator of b. So what should we multiply this last one by to get the b value that we want?
Square root of 2 over square root of 2.
Perfect. Right. And again, this is because earlier we said our b value is square root of 2. Right? So if you think b is 2 or you think b is a different number, you're going to end up multiplying by a different number here, right? And so we want to be really careful about that step. Now we can go ahead and use that table. Okay, so we'll get 1/6 plus 1/3 e to the negative t minus 1/2. Let's see, this corresponds to line number 20 in our table. And so we've got e to the negative 2t cosine of square root of 2 times t minus, let's see, 2 over root 2 times 3, which we can simplify a little bit more if we want, e to the negative 2t sine of square root of 2t. Okay. And I think the only thing the book does after this is it says 2 divided by square root of 2 will give me a square root of 2 on the top. And so that is the only difference between what we have here and what the textbook has. Right. But I'm glad that we sat and went through this problem for a few reasons. I think the first part, just kind of getting in the flow of that, that's a part that I hope for us is we're feeling pretty confident on at this point. Okay, I think we can see that more of the work is sort of in the back end, getting it back into T world. And so I'm glad that we took the time to actually do a matrix solution here, right? So we could have done this with algebra, but I think I heard a few people say, oh, this is like way better, right? Maybe something that is like a very systematic, as long as you put all your zeros in there in the right places, you're gonna be fine, right? And so if you're gonna do this on the exam, absolutely, yes. If you're gonna do this on the exam, just make sure that you've got, show me where you found those from. And then here we go. Then that last place or the last step, knowing that we might still have to do some algebra in some of the other parts so that we can match the table completely. That's a skill that would be really important to practice between now and Thursday. Okay. Other than that, I think just making sure you go over your questions and make sure that you've got your right A value and B value, or A value and N value, making sure you have those accurate before you start to move through the process, I think will also help minimize any mistakes. Okay. All right. So are there any questions right now? All right. Is it okay if I move past the answer now? Okay, cool. All right. So all of this has been talking about translation on the S axis, right? S as in Sam. And so what we're going to talk about today is this idea of translation on the T axis, all right? So sort of like shifting things before we actually do the Laplace transform part. And so in last week's discussion, one of the discussions I had you take a look at the Heaviside function or the unit step function. And so the basic idea of this, which a lot of you wrote about, is that what we have, it's literally like an on-off switch, okay? And this is, I think, pretty cool because in the world of engineering or even applied math in general, when we're thinking about functions, it's important to be able to model different situations with functions. But the reality of a lot of what you might be designing is that we might not want everything to start at the same time. We might want something to start a little bit later or start a little bit earlier than something else. And we want to have that ability to control when the function is on and when it's off. And so that is sort of the whole idea behind this Heaviside function, okay? And so this is a piecewise function, okay? We call it U sub C of T. And if we are less than T is, if T is less than C, then it will be in the off position. Okay, meaning that the function will just be 0. There's no value to it. However, once T hits C, the moment it hits C and from that time forward, now it has been switched on. And I think it's really nice to look at the picture here too, where we can see the function has a value of 0 until we get to C. And then the moment we hit C, now our function has a value of 1. Okay. Now, there are a few other notations that are common for the Heaviside function. So I just want to make sure we're sort of familiar with that notation. We'll go ahead and put that in this box. U sub c of t can also be written as u of t minus c. Okay, the second notation, this u of t minus c, is what makes that, that's where the name translation comes from, because this means that we are shifting the entire function to c, right? C is now our new starting point. Alternatively, we sometimes also use a capital H, like H for Heaviside function. So we might see H of t minus c. Okay, so any three of these ways of writing it is absolutely fine. Okay, but they all mean the same thing. They all mean that you have a function in the off position, and then at a certain time when you're ready, then the function switches on. Okay. All right. Now, you might be thinking, well, this is all fine and good. We can now turn a function to be either in the off position or the on position, but an output of 0 or 1 seems kind of boring, right? Like we can't really do much for that. But when we're thinking about the output values, right? So output values are only going to be 0 and 1, but if we multiply, right? If we multiply by a function, all right, then what we can do is not only have this on-off switch, but we can also say, let's change the value of the unit step function, right? And so what I mean by output values here is, let's say we had 4 times u of t minus c, right? So let's choose that middle notation just to take a look at that. If I have 4 times that, then my output values, I'm going to have it be equal to 0 when t is less than c. But as soon as that we hit c, right, as soon as t is greater than or equal to c, now my function has a value of 4, right? So on off doesn't have to be just binary like 0 and 1. We could also have 0 and 4. Or if we wanted to say, we wanted it to have a negative value. Let's say we multiplied it by -7. Well, what does that do? It changes our piecewise function to be 0 when t is less than c. But when t is greater than or equal to c, now our function will have a value of -7, right? So it doesn't just have to be 0 and 1. It could be 0 and a different number depending on what we multiply by, all right? But this is really the cool part, right? So let's say that we have this function, and this function models whatever we want to model in our applied math life. But we don't want it to start right at t equals 0. Well, we take that, we multiply by the Heaviside function, and now we have the off position, which is just 0. But now when the function turns on, we get the actual function we wanted. All right. And so we can see we've sort of done this translation. We've taken the function and we've shifted it over to start right at t equals c. All right. Arrow in between there. All right. And so this, my friends, is why we have this second translation theorem. Okay, now if you've been reading your textbook at all this summer, you know, and I think I said this up front, that there are typos. Like it often just leaves out letters and you kind of have to guess what things are, but let's put in some of those. So if we have some function that has already been transformed into the Laplace, right? And it's not just a space 0, but a is greater than 0. Okay, so we're assuming that we're shifting over to the right-hand side, right? And that should make sense because if we shifted to the left, we would be in negative time. And if we're thinking about a very applied situation, negative time is sort of not necessarily applicable, okay? But our textbook here uses A, but the A is the same idea as the C that we see in the pictures here. Okay, so we're applying this shift. We are sliding things over to the right. And it turns out that if we have this, then the Laplace transform is just going to be e to the negative as times the Laplace of our original f of t. Okay. Now, if you take a look down at your table, go a little bit further than we've been looking at. So I think we've got it up to like line 23, right? So we spent some time there. Take a look at line 25, 27, 28, 29. All right. We're not going to get to all of those, but like line 25 and line 27, that's really where we're going to be focusing on the rest of today. Okay. All right, so there is a derivation in your textbook. If you're like, where does this translation theorem come from? I think it's a few lines. It's not too bad. If you're interested in the logic, you can definitely take a look at that. Okay. But let's go ahead and do some examples so we have something to sort of sink our teeth into before we leave today. Okay. And so let's go ahead and start with example number 6 here. All right, so example number 6 says, find the Laplace transform of this function. So we have 2 minus 3 u of t minus 2 plus u of t minus 3. Okay. And so what we're going to do is we're going to find the Laplace transform of each piece, right? Because it goes back to that idea of linearity. If things are connected by addition and subtraction, I can split it up into as many Laplace transforms as I want. And any constants I have, I can go ahead and pull out to the front. So if I find my Laplace transform of f of t, I know that's going to give me uppercase f of s. And now I'm going to find Laplace of this term, the middle term, and the third term. So we'll have 2 times the Laplace transform of 1, okay, minus 3 times the Laplace transform of u of t minus 2. Plus, there's no constant to factor out here, so plus the Laplace transform of u of t minus 30. All right, so that linearity principle is pretty handy here. All right, let's find the lines in the table that we need, right? I'll take the low-hanging fruit, and I'll tell you that that first one, you're going to use line number 1. But if you could tell me which lines I should use for the second and third one, that would be wonderful.
Uh, 25, right? Number 25.
Yeah, I think we're going to need 25 here. Number 25. And I might even point out that my C value here is going to be 2. And the third one, I'll also use line number 25, but my C value is going to be 3, right? So setting myself up for success. All right, now we find all the things from the table. So I'm going to end up, the first one is going to end up being 2 times 1 over s, or 2 over s. The second one will end up being 3, and let's see, e to the negative cs, or negative 2s in our case, over s. And then the third one will follow suit. We'll have plus e to the negative 3s over s. All right. So not so bad, not so bad. Let's practice going in the other direction. All right, so now we're going to be looking in the right-hand side of the column and trying to figure out which line matches best with what we have here. All right. So example 7, find the inverse Laplace transform of this f of s. So we know that we need to find the inverse Laplace of 1 over s minus 4 times e to the negative 2s. All right. Which line might we want to use here? Now, knowing that we just saw this sort of second translation theorem, maybe we sort of focus on this side over here, right? Because this is really what we're given, right? If we're trying to read our table backwards, they're really saying, here's what we have on the right-hand side. Now you tell me, where did it come from? Right? And so to me, as soon as I see that e to the negative as, I'm thinking, oh, this is like a translation on the s, or on the t-axis. And so maybe I have to use this idea of the Heaviside function. Okay. And if we go back down to our question here, right? So context clues here, this part is telling me Heaviside, right? But also there is a shift as well, right? There is a shift that is happening. This kind of goes back to what we were talking about yesterday. Here we have a shift, and we are shifting this to the right. Okay. So if we put this together, right, we put this together and we think about what that definition said. The definition of this inverse Laplace of e to the minus as of uppercase f of s is actually going to be the product of f of t minus a times that unit step, or that Heaviside function. All right, so we've got two things going on. Not only are we shifting this, we are also saying, let's add an on-off switch. All right. And so let's do this piece by piece, right? Let's figure out what this part is. That part, I think, is a little bit more straightforward. We're going to have u of t minus 2. But what do we have here? All right, we need to think about what's happening if we were just to read the table for 1 over s minus 4. All right, and if we're shifting that 1 over s minus 4, if we think about what line on the table that is, that goes all the way back up to line number 2. Okay. And so what we end up with here is, knowing that this is line number 2, we're going to end up with e to the 4t. But I'm going to put a little star next to this because that's not quite done yet. Okay, so e to the 4t. And then we have this unit step of t. And then we're going to have our t minus 2. Okay. So this 2 comes from this 2. But the reason why I said let's put a star here is that we're not quite done with this. We need to accommodate for that when we start things, right? The Heaviside function is that switch. That unit step is the switch. So anything before t equals 2, the function is going to be 0. But at t equals 2 and onward, then we actually have our function come into play. And so what we need to do to accommodate for that is we're going to say e to the 4t minus 2 times that unit step. Okay, that way our switch is aligned between all the pieces, that once we hit t equals 2, then the function starts happening, whatever that function looks like. Okay. So before we move on to this third problem, let's just kind of go back to the diagram for a moment, all right, and think about what we're actually doing here. So what we're saying is that we know the function doesn't start until a certain time, right? And so we accommodate for that here. We're saying, all right, we're shifting, here's our on-off switch. At t equals 2, that's when we want the function to turn on. And then we have to say f of t minus c, right? So the function itself also has to be moved over to that starting point. Okay, that's why we have the t minus 2 in both places in our solution. All right, I think we'll probably have time for 1, maybe 2 more examples. Let's kind of see how this goes. All right, so example 8 says find the inverse Laplace transform of s over s squared plus 9 e to the negative pi s over 2. Okay. So let's see what we have here. Let's kind of keep this one up on the screen while we're working on it. We have our inverse Laplace of, whoops. And again, as soon as I see this e to the minus something something, I'm thinking, oh, okay, there's an on-off switch for this function, right? And so my s over s squared plus, I'm going to go ahead and write 9 as 3 squared. Right? And it's because I'm starting to think ahead. I know that that last term is always like an a squared or a b squared. So I want to know what my a and b are. Plus e to the negative pi s over 2. And it's this second term that clues me in that we're going to need the Heaviside function. And all that means is we're going to have some u of t shifted over a certain value. Okay. And in this case, in the previous example, we had t started at 2. But in this case, we're doing t is going to start at pi over 2. Okay. And so if we think about what we have, let's look at which line corresponds to s over s squared plus 3 squared. And I believe that should be, where did it go? It's going to be line number 8, right? This is going to be line number 8, and A is going to equal 3. All right. So if I just apply line number 8, I'm going to have cosine of 3t. I'm going to put a star next to that because this one also needs to be shifted so that when I introduce this heaviside function, everything will be off until the given time. And then after that, then the system will be on. Okay. So u of t minus pi over 2. All right. And now I'm going to go back in. I'm going to make sure I apply the same shift in both functions. So everywhere I see a t, I really need to put t minus pi over 2. And I'm going to get cosine of 3 t minus pi over 2 times that unit step where I'm shifting the function to the right pi over 2. Okay. All right, so these are our 3 examples that we have here. All right. And I think here's what we're going to do for the rest of the time. I think we'll end here for today. And I think when we come back tomorrow, we'll take a look at example 9 and 10. All right, so we'll take a look at example 9 and 10 tomorrow. We'll take a look at one system of equations where we can solve using the Laplace transform. But again, that part, all right, that 7.6 part will not be on Thursday's exam, but example 9 and 10 would be beneficial to go over before Thursday's exam. Okay, so let's kind of pause right here.